An important purpose of structural analysis is to figure out internal loadings at a point in a structure. So in this problem, we're going to determine internal loadings, specifically normal, shear, and moment, at points inside a beam. The key concepts we're going to work on are calculating reactions for determinate structures and calculating internal loadings at a cut in a structure. Let's take a look at our beam. We're going to determine the normal force, shear force, and moment at points C and D. And D is very close to a concentrated force applied to the beam. We can't calculate shear exactly where the point force is applied, so we have to specify whether we're just to the left or just to the right, and in this case we're just to the right of the 5 kip load. So let's take a look at our approach. Our first step, we're going to bound the solution. Which is going to give us limits on what our answer could be. We'll compare our final answers to make sure they're within the limits. We're going to confirm determinacy and stability. Because if it's not a determinate member, it changes how we approach structural analysis, and if it's unstable, sometimes we can't perform structural analysis. We're going to calculate reactions. Then we're going to cut it at C, and then we'll apply equilibrium. In order to get those internal loadings. Step 5, we'll then go and cut it at D and apply equilibrium. And step 6, we'll check our answers to make sure they're within the limits. Step 1, we're going to bound the solution. This is going to give us limits on the magnitudes of the shear and moment at the various points in the beam. Since all loads are in the same direction, the shear cannot exceed the total applied load. And that's an absolute worst case scenario. So our limit, upper bound, which we really don't expect to get to, 5 kips per foot times 12 feet, gives us the total force applied by the distributed load, plus 5 kips downward is 11 kips total load, and so that's our upper limit on the shear, but we really don't expect the shear at C or D to reach those limits. The lower bound limit, well, can't be less than 0. We don't expect it to get too close to that either, considering that the points C and D are getting close to the supports where the shear tends to be highest. Now for moment. Using the same process we're about to follow in this problem, you could derive that the peak moment in a uniformly loaded, simply supported beam is omega, the distributed load, times the length of the beam squared, divided by 8. I want to point out this is worth doing as an exercise and then memorizing, because omega L squared over 8 is a quantity or a formula that we'll use over and over again in structural analysis and structural design. Since the loads are applied closer to the supports, when we approximate the total load as uniformly distributed across the beam, we're going to get an overestimate. And that's worth repeating. Since our applied distributed load is closer to the support, it doesn't create as big a peak moment as if that same distributed load was applied closer to the middle. And our concentrated force is over close to the support. We're going to take all of this 11 kips and uniformly smear it across the beam, which is going to give us a peak moment, omega L squared over 8 here, that should far exceed anything we actually see at points C or D. So our M, upper limit, is the 11 kips divided by 24 feet. That's the equivalent distributed load across the entire beam. L squared, 24 feet squared over 8, gives us 140 foot kips as our upper limit. Our lower limit, again, is going to be 0. We don't expect 0, and we definitely expect something less than 140 foot kips. Now step 2, let's confirm that this is a determinate and stable structure. Do that, let's label our reactions, our unknowns. We have AY and AX because A is constrained by a pin. We have a roller at B, which provides only vertical reaction, BY. So my unknown reactive forces are 3. Number of free bodies, 1. So we compare 3 and 1 times 3, those are equal, therefore it is determinate. We need to check the reactions to ensure that it's stable. The reactions are not parallel, they're not concurrent, therefore it is stable. Now I'll point out the formula for peak moment that we used for a uniformly loaded, simply supported beam, omega L squared over 8, is for a beam that is determinate and stable. Simply supported meaning it's supported by a pin on one end, a roller on the other. All the loads are in between. But it was still worthwhile to go through and demonstrate this one more time. We're ready to do some calculations now. Step 3, let's get the reactions. We'll start with summing forces in the x direction. choose to the right as positive. And the only thing in the horizontal direction is AX, so that reaction is 0. Now let's sum moments about point B. We'll choose counterclockwise as positive. We get a contribution from AY that's in the opposite direction through 24 feet. The distributed load acting over 12 feet, which is the total force. Its distance from point B is 18 feet. And the concentrated force, 5 kips, acting through 6 feet. We get a vertical reaction, AY, of a positive 5 3/4 kips, which means it's in the direction drawn. Now let's sum forces in the Y. We'll choose up as positive. We know that we have the reaction at A and its magnitude. We have the distributed force acting over 12 feet. The concentrated force and the reaction at B. BY is also positive, so it is in the direction we drew it. 5 1/4 kips. Now we're ready to cut the structure. And apply equilibrium so we can get the internal loadings at point C. We're going to cut it right there, and I'm going to use the left piece. Since it has fewer forces acting on it, I'm less likely to make a math error. So I'll draw my left piece, my vertical reaction at A, 5 3/4 kips, my horizontal reaction of 0. It is a 6-foot long piece. We have our unknown shear at point C, our unknown moment at point C, and our unknown normal force at point C. And we also have our distributed load of 1/2 kip per foot. Let's apply equilibrium in the x direction. We'll take to the right as positive. There's nothing from the reaction at A, so it's only the normal force at C. Now vertical equilibrium. Choose up as positive. Get the contribution of the reaction at A. The distributed force, but there's only 6 feet of it in our free body, and the unknown shear at C. So the shear at C is a positive 2 3/4 kips. Remember, positive is denoted on this side of the cut is down, but if we'd used the other free body, the other side of the cut, positive would have meant up. Now some moments. We'll go about point C, and I'll choose counterclockwise as positive. Have the contribution from the reaction at A going in the other direction. Contribution from the distributed load. Again, there's only 6 feet of it, and it acts at 3 feet. And the unknown moment at C. We solve that to find moment at C is 25.5 foot kips. And again, since we're keeping the left half, or the left piece, for the free body, we said positive moment is that way. If we'd use the other piece, positive moment would have been clockwise. Now let's jump to step 6. And our check with the limits. Said the shear had to be greater than 0 and less than 11 kips. And we got 2 3/4, so it is. Said that the moment had to be greater than 0 but less than 140 foot kips, and we got 25.5, so that also checks. Good. So we have confirmation that our results are reasonable. Now let's take a look at the cut at point D. And apply equilibrium. Remember, point D is just to the right of the 5 kip load. We're going to use the right piece for our free body because it has fewer forces. We have the vertical reaction at B, 5 1/4 kips. Our piece is 6 feet long. We have our unknown shear at D, our unknown moment at D, and our unknown normal force at D. We have no applied loads to the piece. So we apply horizontal equilibrium. This time I'm going to take to the left as positive. So we have the normal at D, but that's our only contribution in the horizontal direction, so the normal force is 0. Now let's sum forces in the y direction. Choose up as positive. We have the unknown shear at D and the vertical reaction at B. So the shear at D is a negative 5 1/4 kips. And again, remember, for the right free body diagram, up is a positive shear, but if we had chosen to use the left free body diagram, our shear would have been drawn down. Let's sum moments. We'll go about point D. This time I'll go clockwise as positive since it is my choice. I think this will make it a little easier. We have our unknown moment at D. Contribution from the reaction is in the opposite direction. Our moment at D is a positive 31.5 foot kips. Again, remember that for the right piece, we said clockwise is a positive moment. If we'd have kept the left free body diagram, we would have drawn it as counterclockwise. Now step 6. We'll check our results with the limits. So we said the shear at D had to be greater than 0, and that's the magnitude of the shear at D, but less than 11 kips, which it is. And the moment at D said had to be greater than 0, but less than 140 foot kips. And that it is. Now let's review what we did. We started by bounding the solution. If we can discover or approximate upper and lower limits for our answer, then it helps give us some confidence when we're all done, when we find that our results are within those limits. We calculated the total applied load to the beam and knew that the peak shear anywhere in the beam had to be less than that total applied load, probably much less, but it had to be bigger than 0. So we had our limits on shear. To get the limits on moment, we know that the minimum moment is 0, but to get the upper limit, or the maximum moment, we took the actual applied loads, added them all up, and then distributed them uniformly across the simply supported beam. We used our knowledge of uniformly loaded simply supported beams to get the peak moment. Under those conditions, the peak moment is omega L squared over 8. And we know that taking the actual loads and distributing them uniformly across, which brings more load to the middle region, which causes a higher peak moment in the middle region. So we know that our 140 foot kips would be an upper limit, because we're looking at points away from the middle region and because our real loads are farther away from the middle region. We then confirmed that our beam is determinate and stable. We applied equilibrium to calculate the reactions. And we cut the structure at C and applied equilibrium to the left piece. We found that the normal force at C is 0. The shear was 2 3/4, and the moment was 25.5 foot kips. We then checked it with our limits. We were well within our limits, and as expected, the shear and moment were well below the upper limits. So we have reasonable confidence that these are reliable numbers. We then moved to point D, cut it, kept the right piece for a free body diagram, and applied equilibrium. Found that the normal force is 0 here as well, that the shear is negative at D, which is a point just to the right of the 5 kip applied load, and calculated the moment to be 31.5 foot kips. Again, we checked with our limits, found that these forces, internal loadings, are also within the limits we calculated, well below the upper limit values, so we have confidence in these numbers as well. Well done.